All right, let's get right to it. As someone managing AI projects, the one question that comes up over and over again is how do we actually scale? How do we build all these systems, things like APIs, data pipelines, search engines, so they can handle thousands of users at once without just falling over or costing an absolute fortune? The answer, really, it all comes down to understanding how Python handles concurrency. So today, we're breaking down asynchronous versus traditional threading and why this choice is so fundamental for building real, high-performance production systems.
So before we can even talk about the solution, we've got to wrap our heads around the problem we're up against. And honestly, the biggest bottleneck in almost any system that deals with networks or databases is simply waiting.
Okay, picture this, a super futuristic restaurant run entirely by robots. And the rule is simple, one robot for every single table. Sounds pretty efficient, doesn't it? But hold on, let's really think about that. What are the diners doing most of the time? They're looking at the menu, they're talking, they're eating, and the robot is just standing there, idle, wasting electricity, waiting for someone to ask for the check. Well, that's exactly how a ton of traditional backend systems work, one thread per request. And most of those threads are just sitting around, twiddling their thumbs, waiting on a database or some other network call to finish.
And here's where it gets really expensive. Why is all that waiting so bad? Well, each of those robot threads is what we call stackful. Think of it like this. Every thread needs its own big, heavy backpack, its own chunk of memory, its C-stack, just to remember what it was doing. And when the operating system has to switch between all these waiting threads, it's like making them swap these heavy backpacks over and over. That's a context switch, and it's a super slow, heavy operation. For anything doing a lot of I/O, yeah, it's just a huge waste of resources.
Okay, so if the army of waiting robots is a terrible model, what's the better way? Well, this is where Asyncio comes into the picture, and honestly, it's a brilliant solution.
So forget the army of dumb robots. Instead, imagine just one hyper-efficient robot. It's like a master chef and an orchestra conductor, all rolled into one. This is the Asyncio event loop. It runs in just a single thread, but it is an absolute master of multitasking. The second a task says, hey, I'm about to wait for the database, the event loop doesn't hang around with it. Nope, it instantly pivots to the next task that's ready to go. The CPU is never idle, not for a second.
So how does it pull off this magic trick? Well, the secret sauce is something called coroutines. Let's dig into what makes them so different from those clunky old threads.
And this right here shows you the absolute core difference. Remember that heavy backpack the thread was carrying, the stackful one? Well, a Python coroutine is stackless. It's like it has a tiny weightless fanny pack instead. Its state is stored really efficiently on what's called the heap. This means it can just pause itself, hand control back to the event loop, and then pick right back up where it left off with practically zero effort. That's why they're so incredibly lightweight. You can seriously run thousands, even tens of thousands of these in a single thread. It's a total game changer.
So let's break down the execution. A normal function, your standard def block, is like a train on a single track. Once it starts, it goes until it's done, and nothing else can use that track while it's running. But a coroutine, the async def one, is different. When it gets to an await keyword, it's like it's pulling over at a rest stop. It's telling the event loop, hey, I'm going to be here for a minute. Feel free to let someone else use the highway. It's totally non-blocking. This is what we call cooperative multitasking, and it's the heart of how Asyncio works.
And it's not just this one little trick. Async I/O is a whole platform, a whole stack of tools. You see here at the very bottom, you've got the basic building blocks, coroutines in the event loop. On top of that, you get things like tasks and futures to manage what's happening. Then you've got executors, which are super important for dealing with old-school blocking code. And right at the top, you have these powerful, high-level tools for things like network streams. It's a complete toolkit for building really scalable applications. Okay, that's the theory. But how does this actually play out in the real world, in our production systems? Well, there's one golden rule, the single most important thing you have to remember. Seriously, if you walk away with only one thing today, let it be this. If you block the event loop, you block everything, your whole system. Remember, all those thousands of tasks are taking turns on that one single loop. So if one of them decides to do a heavy, slow calculation and doesn't politely hand control back, boom, your entire application just freezes solid. It's catastrophic.
So what do? Simple. You offload it. Any task that's actually working hard, doing heavy computation, not just waiting, you have to hand it off. You use something called an executor, which basically runs that blocking code in a totally separate thread pool. This keeps your main event loop completely free to just zip around, handling all the I/O. It's the most important distinction to make. Asyncio is for waiting, and threads are for working.
All right, let's look at a super common example where this makes a huge difference. High-traffic databases. Let's say Postgres.
So in the async world for Postgres, you've basically got two main contenders. First, there's async PG. This thing is a beast. It's written in low-level C and Python. It speaks the database's native binary language. It's the speed demon. It is built for one thing: raw, unadulterated performance. Then you've got Psycho PG3. This one's a bit different. It's pure Python, and its big selling point is flexibility. It has one API that works for both old-school synchronous code and new async code. That makes it way easier to switch over if you have an existing project.
And you can see the trade-off right here. When it comes to just pure raw throughput, yeah, async PG is the undisputed champ. But, for a lot of projects, that 20% performance gap might not be the most important thing. Maybe having an API that your team already knows is more valuable. It really comes down to what you need. Are you squeezing out every last drop of performance, or do you need a tool that's a little more flexible and easier to work with?
Okay, now let's shift gears and look at the future, because something huge is happening in the Python world that's going to change everything about how we think about this stuff.
So for its entire history, Python has had this thing called the Global Interpreter Lock, the GIL. You can think of it as a gatekeeper that only lets one thread run Python code at any given moment. Even if you had a 32-core processor, only one core could be running Python at a time. It's been a huge limitation. But now, the GIL is on its way out. It's becoming optional. And this opens the door to what's called free-threaded Python. This is true parallelism. We're talking multiple event loops running on multiple threads on multiple CPU cores, all at the same time. This is a seismic shift.
And we're not talking about small incremental improvements here. Just look at this number. Early benchmarks for network traffic show a speedup of almost 2.7 times. That is massive. It completely redefines the performance ceiling for Python.
Okay, so let's put this all together. How do you choose the right tool for the job? Here's the cheat sheet, the main takeaway. If your code is going to spend most of its time waiting for networks, for databases, for files, Asyncio is your best friend. It's the king of high concurrency I/O. But if your code is going to be working, crunching numbers, processing data, you have to use threads or even multiprocessing. You have to keep it off that event loop. And for all that old code that just blocks, that's what executors are for. It's all about picking the right tool for the job, waiting versus working.
Now, putting my AI project manager hat back on, this isn't just some low-level technical detail. This is business strategy. This is how we build APIs and vector search that can actually scale. It's how we handle thousands of users without our cloud bill going through the roof because we're not wasting CPU cycles. At the end of the day, this is how we build the kind of reliable, fast AI systems that actually deliver value.
So I'll leave you with this final thought. For years, we've lived with this neat little dividing line. Async for waiting, threads for working. But now that the GIL is disappearing, that line is starting to blur. We're entering a world of true parallelism. So the real question is, how are you going to combine these two worlds? What new kinds of architectures become possible when you can mix and match high concurrency I/O with true multi-core processing? That's the challenge for all of us building the next generation of systems.